So, how does your brain do it? How does it take all the light and sound and everything else from the world and build the solid reality you experience, well, right now? The answer, it turns out, is a lot weirder than you'd probably guess. Okay, let's dive in.
And we're going to start with a question that sounds kind of impossible. Imagine you're looking at an object. You can see its exact shape, the color, the way light glints off of it. You see it perfectly, but you have absolutely no clue what it is. It's just a thing, a collection of features with zero meaning. How could that even happen?
Well, this wasn't a hypothetical for a patient known in medical literature as DF. After a tragic case of carbon monoxide poisoning, something very strange happened. Her eyes worked. She could see all the little details, but her ability to actually recognize the shape of an object was just gone. The condition is called visual form agnosia, and her case was about to change everything we thought we knew about the brain.
To really get what was happening inside DF's head, first we have to peek behind the curtain at one of your brain's most brilliant secret tricks. See, when you look at anything, your brain doesn't just take one big mental picture. No, it's way smarter than that. It instantly splits the job into two totally separate, parallel streams.
So meet your two visual streams. First up, you've got the ventral stream, but we'll just call it the what stream. Its whole job is to figure out what you're looking at. Is that a coffee cup? Is that a friend's face? It handles the form, the color, all the identification stuff. But at the exact same time, you have the dorsal stream, or the where stream. Its job is completely different. It's tracking motion, location, and, this is the really key part, it's guiding your body's actions toward that object.
So what this really means is that seeing isn't just one thing. It's a duet. One part of your brain is asking, what is that thing? While a totally different part is asking, okay, where is it and how do I interact with it? And they're both working together all the time, completely behind the scenes, to build the world you see around you.
Okay, so let's get back to patient DF, because her case is where this all gets really interesting. It's the absolute best proof we have that these two streams are really and truly separate. Right, so her diagnosis was visual form agnosia. That carbon monoxide had specifically targeted and damaged her what pathway. The part of her brain that's supposed to identify stuff was broken. She could see all the pieces, but her brain couldn't put them together to see the whole. But what about her where stream? Was it still working?
This is where the researchers came up with a truly brilliant experiment. First, they showed DF a slot that was tilted at an angle. They handed her a card and said, just hold the card to match the angle of the slot. Simple, right? But her attempts were totally random, all over the place. Her what stream had no clue what the orientation was. But then came the twist. They changed one little thing. They said, okay, now post the card through the slot. And this is the mind-blowing part. Her hand moved flawlessly. It rotated the card to the absolute perfect angle and slid it right in without any hesitation.
And that right there, that's the smoking gun. Her conscious what system, the part she had access to, had no idea what the angle of the slot was. But her unconscious where system, the one that guides her actions, it saw it perfectly and knew exactly what to do. Two separate systems, one broken and one working perfectly, inside the same brain. Just incredible.
Now here's the really cool part. This whole what versus where idea isn't just for vision. Your brain uses the same divide and conquer strategy for your other senses too. Let's talk about hearing for a second.
So how do you know where a sound is coming from? You just kind of know, right? Well, your brain is using a few clever tricks, and one of the big ones is called the inter-aura level difference. All that means is the tiny, tiny difference in how loud a sound is when it hits each of your ears. Think about it. If someone calls your name from off to your right, the sound has a direct path to your right ear, but your own head gets in the way. It actually blocks some of the sound waves from getting to your left ear, creating a sound shadow. That makes the sound just a little bit quieter on the left, and in a split second, your brain uses that tiny difference to pinpoint exactly where the sound came from. And boom! There it is again, the same exact principle. Your auditory system has what pathways that are busy figuring out the pitch and the tone, trying to identify what the sound is. Is it a voice? A car horn? At the same time, it has totally separate where pathways, using tricks like the sound shadow to build a 3D map of sound all around you. What versus where, all over again.
So, what about touch? Well, it turns out your skin isn't just a simple wrapper. It's an incredibly complex interface, absolutely packed with a whole team of specialist receptors, and each one is designed to pick up a totally different kind of information.
Okay, so let's meet the team. You've got Merkel discs. They feel sustained pressure, like the weight of your phone in your hand.
Then there are Meissner corpuscles, which detect light fluttering touches. Ruffini endings sense when your skin stretches. And Pacinian corpuscles, they're the experts in deep pressure and vibration. Each one is a specialist, sending its own unique signal up to your brain.
And what's really wild is how these receptors are distributed. On your fingertips, for example, you can tell two separate points apart even if they're just 2 or 3 millimeters from each other. But try that on your calf. Those 2 points would need to be almost 40 millimeters apart before you could tell it's not just one poke. It shows you just how much brain power is dedicated to the super-sensitive information coming from your hands.
And we're not done. There's a completely separate system just for temperature. These receptors have tiny channels that pop open when they detect heat. And here's a super cool, kind of weird fact. The exact same receptor that detects painful heat is also triggered by capsaicin, the chemical that makes chili pepper spicy. That's why eating a hot pepper literally feels hot. You're hijacking the exact same neural pathway.
Okay, so we've seen how our brains take reality and just take it apart. Sight gets split up, sound gets split up, touch gets split up. And all of that brings us to one of the biggest, most fundamental questions in all of neuroscience.
So, if you remember one thing from all this, let it be this. Your brain's first move is always to deconstruct. It shatters every single experience into its basic parts. Vision becomes shape, color, and motion. Hearing becomes pitch and location. Touch becomes a whole menu of different feelings. At first, nothing is perceived as a whole.
Which leads to the final and kind of profound question. If your brain is constantly smashing the world into all these separate little pieces, how do you experience it all as one single, seamless, unified reality? I mean, when you look at a cup of coffee, your brain is processing its shape, color, location, temperature, and the feeling of it in your hand all in different places. So, how do you just see a cup of coffee?
This question actually has a name. It's called the binding problem. It's the monumental challenge of figuring out how the brain takes these dozens of separate streams of information and weaves them back together into the single, coherent consciousness you're experiencing right this second. And the truth is, we don't know how it works. It remains one of the greatest unsolved mysteries in all of science.